going to dive into something you probably use every single day but never really think about, the humble Ethernet cable. It's kind of the unsung hero of our digital lives, right? That physical link to the internet that we just plug in and forget. But inside this simple-looking wire, there's a whole world of fascinating engineering. You know, for anyone who's ever worked in IT or studied for a networking certification, making one of these cables from scratch is, well, it's a rite of passage. It's a fundamental skill that shows you really get the building blocks of how a network actually works. And look, that's a totally fair question. I mean, you can just walk into pretty much any store and buy one for a few bucks. So why on earth would you go through the hassle of making one yourself? Well, as it turns out, there are some really good reasons. Okay, for starters, custom lengths are a game changer. If you're setting up a server rack or running a cable through a wall, you want it to be the exact length you need. No more messy coils of extra wire tucked away. Then there's on-the-spot repairs. Those little plastic clips on the end, trust me, they break. And instead of having to replace a whole 50-foot cable run, you can just snip off the end and put a new one on in about 2 minutes. And finally, yeah, it's just cheaper. If you're doing a big project, buying a big spool of cable and making your own is way more economical.
So to really appreciate what we're about to build, we kind of have to understand what's going on inside. So let's do it. Let's peel back that outer jacket and really take a look at the anatomy of an Ethernet cable.
All right, so the two main types you're ever going to see are unshielded twisted pair, we just call that UTP, and shielded twisted pair, or STP. UTP is what you've got in your home or office for sure. Its only protection from interference is just the way the wires are twisted. Now, its tougher sibling, STP, has this extra layer of foil shielding around the wires. Think of it as armor, making it perfect for places with a ton of electrical noise, like a factory.
So why are the wires all twisted up like that? It's not just to look neat. The two biggest enemies of a clean data signal are EMI, that's electromagnetic interference from stuff like power cords, and something called crosstalk. Crosstalk is basically when the signal from one wire bleeds over and messes with the signal on the wire next to it. And the solution is brilliantly simple. Just twisting the pairs of wires together actually cancels out most of that noise. It's low-tech genius. But that brings up an even bigger question, right? We're talking about 8 simple copper wires. How in the world do they send a high-def video or let you play an online game with your friends? How do they actually speak the language of computers? Well, it's actually a super elegant trick with electricity. To send a binary 1, the device on one end sends a little pulse of positive voltage down the wire. The other end sees that positive voltage and thinks, okay, got it, that's a 1. Then to send a binary 0, it just does the opposite. It sends a pulse of negative voltage. Now imagine doing that, flipping between positive and negative millions of times every single second. That's how you get data. Now, for this all to work, you need some organization. Think about it. For a conversation to happen, one person has to talk while the other listens. It's the same here. A device like your computer is literally hardwired to talk or transmit on pins 1 and 2, and it listens or receives on pins 3 and 6. A network switch does the exact opposite. It listens on 1 and 2 and talks on 3 and 6. And that little detail is absolutely crucial.
And that is exactly why the most common cable in the world is the straight-through cable. The name tells you everything you need to know. The wire on pin 1 on one end goes straight through to pin 1 on the other end. Pin 2 goes to pin 2, and so on. It's a perfect design for connecting a PC to a switch because the PC's talking pins line up perfectly with the switch's listening pins. It's a perfect match.
But what if you wanted to connect two computers directly to each other? Well, then you'd have a problem. They'd both be trying to talk on the same wires and listen on the same wires. It'd be like two people talking at the same time, no one's listening. The old school solution to this was the crossover cable. It literally crossed the wires inside, connecting the talk pins on one side to the listen pins on the other. Pretty clever. So why have you maybe never even heard of a crossover cable? Well, the answer is a little piece of tech magic called Auto-MDIX. Basically, all our modern gadgets are smart. They can automatically tell what they're plugged into, and if they sense a problem, they'll just swap their own internal wiring on the fly. It's a brilliant little feature that has made the crossover cable pretty much a museum piece.
So even with all these smart devices, we still need a universal rule book, right? A common language for how to arrange these colored wires so that everything just works together. And the most common standard by far, the one we're going to follow, is called T568B. And here it is, the secret recipe. Looking at the connector with the little clip facing away from you, the order is white-orange, orange, white-green, blue, white-blue, green, white-brown, and brown. Now, it might look random, but it's not. The orange and green pairs, our talk and listen wires, are intentionally separated by the blue pair to cut down on that crosstalk we mentioned. This is the sequence you've got to burn into your brain.
All right, time to actually build this thing. Step 1, strip about an inch of the outer jacket and untwist all those little pairs. Step 2, get those wires flat and arrange them in that T568B color order. Step 3, hold them super tight and give them a nice, clean, even trim. Step 4, this is a tricky bit, carefully slide them into the connector. And finally, step 5, pop it in the crimping tool and give it one good firm squeeze. And that's it. You've just made a network connection.
Now, you just have to do that exact same process on the other end of the cable. As long as both sides are wired to that T568B standard, you've got yourself a perfect straight-through cable. Now, before you go plugging it into anything important, it's always a good idea to test it first.
Now, even if you make the most perfect cable in the world, this technology has one big limitation, and it all comes down to this number, 100 meters. That's about 328 feet.
Yep, that 100-meter mark is the absolute maximum length for a standard copper Ethernet cable. If you try to go any longer, the electrical signal just starts to get weaker and weaker. It's called attenuation. It leads to slow speeds and lost data. It's like trying to shout across a huge field. Eventually, your voice just fades out. If you need to go further than that, you have to jump to a totally different technology, like fiber optics. And that kind of brings us full circle, doesn't it? We started with what looks like a simple cord, and we ended up talking about twisted wires, electrical voltages, pin assignments, and color codes. It's pretty amazing how much is going on inside. It really makes you look around and wonder, what other everyday tech that we totally take for granted is hiding this much magic just under the surface?